Hi everybody, this is our first lecture in our physical activity section, our last section. And this first class is going to give you an overview of the assessment of physical activity and sedentary behaviour. We'll touch on both. So if I was to ask you, how did you spend your Sunday? I'd get a variety of answers. Physical activity and sedentary behaviour are incredibly variable, both within individuals, but also particularly between individuals. So this is just a graphic that gives you an example of two women, two men, and how they spent their day. And if we went from when they got up in the morning to when they went to bed at night, you can see that they chop up their day in different ways. If we could think of that sedentary time, active time, moderate to vigorous activity, and then what we'd call incidental or non-exercise activity, thermogenesis, all the other things you do that burn energy but aren't formalized, structured exercise or sport. And that would be our breaks in sitting, if you like, or breaks in sedentary time. And so you can see that Anne here has had an incredibly sedentary day. She got up, she sat, she drove to work or drove somewhere, sat for the rest of the day, drove home, sat and then watched TV and went to bed. Mike has had large periods of sedentary in his day, you can see that. But he did play sport and he broke up his sedentary time in the morning. So small amount of sedentary breaks or non-exercise activity, thermogenesis, neat, and a little chunk of exercise. Kim did the same amount of exercise, so did Joe, but you can see how they've accumulated different breaks, which starts to reduce the sedentary time. And really, I'm going to focus on Joe because you can see that although he had moments of sedentary in his day, the grey bars, lots and lots of breaking of sedentary time, an exercise bout, and the same amount of sedentary time in the evening, but all these breaks mean that his non-exercise activity thermogenesis is so much higher than anybody else's. So how do we go about measuring these things? We don't self-report, as you know, as a problem child, but how do we go about capturing the breaks, the actual structured exercise or sport, as well as those sedentary times and when you go to bed? So I'm going to give you an overview of how we go about assessing and primarily physical activity, but I'm going to also talk about sedentary behaviour because they are one and the same these days in terms of what we're trying to capture. And I'm going to give you an overview of the objective options that we have, and then of course, we'll just touch on the subjective. So first of all, this is what we talked about last Wednesday, but let me just go over this. What is physical activity? Well, remember we got a really nice definition where all human movement can be categorized as anything that expends energy, and we can plump that into what we call physical activity. So everything you do that expends energy from movement of large muscle mass is physical activity. And it can be exercise and it can be non-exercise. This picture here is actually me and my sister running in the Standard Chartered half marathon in Hong Kong, and my graduate student found that there was a few thousand people, but we're the only two people talking. I think we talked the entire way. I think that might have been non-exercise, but we did jog slowly. But generally this is structured. We've chosen to do this long bout of exercise. We've done exercise to prepare us for it. And non-exercise is all the other things you do in your day, walking to the bus, walking to work, just being, doing your housework, making your bed, all the other things that you do that expend energy but aren't structured, and the two together make up physical activity. So when we take this kind of global construct of physical activity is a behavior that you have. And, you know, what we're saying is it is a behavior that results in energy expenditure, the energy cost of that behavior. So essentially, whatever we do to measure it, we're trying to extrapolate it back to the energy cost. And we have all these different ways of trying to get there. Ideally, if you really wanted to measure energy cost, you would measure energy cost. You would use calorimetry, but you can't have people walking around all the time with a calorimeter, like a gas analysis mask or mouthpiece. We can put people into rooms which are calorimeters, and they can live there for a while. But again, it's not ecologically valid. We don't live in a box which just measures the caloric output of everything we do. There is a field measure, doubly labelled water, where you drink an isotopically labelled water, and then we collect your urine for 10 days, and we measure the flow of that isotopically measured water, how much it's excreted in terms of urine, and how much it's utilised, and the utilisation happens through physical activity. So we get a kind of field measure of caloric cost of all the things you do. But it's expensive, and you need very sophisticated machinery to be able to actually analyse the urine. So we then go to the next best thing, which is various ways in which we could capture energy in the field: heart rate, body temperature, ventilation, and really we're thinking of heart rate and wearables. So heart rate and motion detection are our two major sources of field measures, direct measures of field energy expenditure. We can do other things. We could actually record people. We could follow them around and write down everything they did, but not, again, really ecologically valid. People change their behavior if they know they're being watched. And then we have the indirect measures, which would be a questionnaire, the self-report measures. And of course, what we're really interested in is whether this thing we call physical activity and the energy cost associated with it, if we can capture that, we can start to look at the relationship between the amount of energy you expend per day and various health parameters. So I'm going to focus on motion detection and heart rate as my main two markers of physical activity, but I'll also touch on sedentary behavior, as I said. So if we look at the measurement of these movement devices, as well as heart rate, you can see here the room calorimetry, when you put you in a box that can measure all the caloric output of everything you do while you're living in that box, to the doubly labelled waters, to the indirect calorimetry, which is your gas analysis, into these movement sensors. And of course, this is the very precise way, but not particularly easy to measure. And these are the really easy ways, but not particularly precise, like self-report. So heart rate and movement sensors fall somewhere on this line. I think that this is an old picture. The sophistication of these devices now means that they're probably about the middle now. They're almost as good as indirect calorimetry, but remember, they don't actually measure calories, which is why they fall low. And really, we're going to concentrate a little bit on indirect calorimetry because we do use it for calibration. So what is indirect calorimetry? Well, you've done this, you've used it in VO2 max. If you measure VO2, you can get a caloric cost. You have to use a mask or a mouthpiece for some description and actually measure the oxygen uptake. And this is a picture of a child doing a resting oxygen uptake measure. We're trying to just find out what resting metabolic rate is. They have to be awake, but really relaxed, so they would watch a movie of their choice. You can see the mask and the gas analysis occurring here. We can do that while you're moving. So this is running on a treadmill, same aperture, but now using a mouthpiece and nose clip. And then we can use that to make sense of our data. But this is pretty expensive. This isn't $500,000. This should be $50,000. But it would cost $50,000 approximately to buy the setup for the gas analysis machine. So it's not a very user-friendly type of method, but it is useful. So if we have somebody exercising, we measure their heart rate, we measure their oxygen uptake, we can plot their individual calibration. You remember how we did our plots of the data, the slopes? We do the same thing, except now we do VO2 over heart rate. We plot the slope. We get the equation, and that's to predict VO2 from heart rate. And this is 0.035 times heart rate, whatever the heart rate was. And you can solve the equation and get the exact VO2. So once you've got this predictive equation from that individual's plot, then we can collect heart rate in the field and we can convert it to VO2 and subsequently to calories. So we can use this heart rate VO2 calibration curve to get a, if you like, a calibration of what does our heart rate really mean in the field in terms of caloric output. So let's look at heart rate monitoring. I started my PhD, and that's the devices I used. I used the polar heart rate monitoring on the kids that we measured during my PhD, and subsequently during my time working in Hong Kong, and subsequently now in a training study where we're using heart rates again. So back then we had to wear a chest strap. This is a telemetry system, like a radio telemetry. This picks up the signal and sends it by radio telemetry to the watch, and the watch captured the heart rate. This has become more sophisticated, and the devices you now wear at the wrist have photo sensors on the back of them. You can see the little flashing lights if you wear a smartwatch, and that is an optical reader of your heart rate. So that is no longer the necessity to wear a chest strap in day-to-day wear. We can actually receive the data from the wrist reception of an optical reading of heart rate. If we were to plot all the heart rates that we receive across the course of a day, in an ideal world, it would look a little bit like this. We would have known that on the basis of the VO2 heart rate calibration curve, that and their VO2 max test, that whatever their maximum was, that this is above this is approximately vigorous exercise between 140 and 160, and this kid is moderate exercise, and between 120 and 140 is light intensity exercise. So the majority of their time is spent below 120, mostly in rest with these little spikes. 5% in light, 6% in moderate, and 7% in vigorous in this particular child. They don't generally look like this. This is quite a large activity bout. This looks like exercise lasting quite a long time, quite structured. This is probably walking to school. This is probably lunch break. These are probably breaks in the middle of the day, and this is something going on once they leave school, probably exercise or sport. But for many kids, the heart rate trace doesn't look like that. It's barely, you can see anything above baseline. The deficit with heart rate is really being able to distinguish sedentary time from active time. So you can see that we might find a resting heart rate in here, but there's a huge cluster of heart rate below that threshold of 120. But we don't know whether this is seated and just maybe excited by watching a movie down in this level, or whether that's actually active time, low activity NEAT. So heart rate isn't great for detecting these, distinguishing between sedentary and active time, but it's really quite good at doing the exercise. So we're going to go on to movement sensors. So accelerometers are, they've been in the field a long time. We started using these RT3s back in the early 2000s. We're currently using a Genie Active. They used to always be worn at the waist. The Genie Active is worn at the wrist. Wrist wear is easier in the sense that you don't have to take this off. You can wear this watch 24/7. It's waterproof. You take it off, you forget to put it back on. Accelerometers measure acceleration. They measure actually gravitational units, and we create a kind of arbitrary unit for the device to give us. They can come with different axes. Nearly all of the ones we use now are what we call triaxes. They can measure forward to backward movement, up and down movement, side to side movement. So they can pretty much capture everything you do. We've measured placement. Waist worn or wrist worn. Well, waist worn might be better, but you have to take it off. So wrist worn allows you to have better wear time. Calibration, I'll mention that in a moment. Buttons are important while working with kids. Anything with buttons that they can turn it off is a problem. These buttons, it doesn't matter how many times they press them, they cannot alter this device. It also tells them nothing. These buttons, this device, if they touch these buttons, they could turn the device off. So we used to have to strap a plastic layer over these to stop them doing that. And then the last piece that I'll come to is called epoch, or the sampling time. And kids move in very short bursts of activity, 2 to 5 seconds. So you need to have this thing sampling at least second by second. So you have to tell the device, or you have to calibrate the device. You need to know when it gives you these counts. This is an example of counts per second. I mean, they don't mean anything. It's not like a heart rate that has meaning. So you have to run a calibration study to be able to make sense of what the data tell you. This is one that we did a few years ago, where we got the kids in and they sat for a period of time, then they did some light activity, whatever it was, and then they did moderate activity tasks, and then they did vigorous, which would have been running on the treadmill. And then we create these cut points so that when we get the data back, we say everything over 68.5 is moderate or high, anything between 31 and 68.5 is low to moderate, and so on and so forth. So we try to create these boundaries so that we can interpret the data. So you can't use an accelerometer without having a calibration or cut points. In the field, a lot of people will use somebody else's cut points, but they really should be population specific. So just an example of the data, heart rate data, you kind of understand. If you're running really hard, your heart rate will be over 160. We get heart rate data, but it's harder, as I said, to make sense of accelerometry data. So this was work we did with lean and obese kids. This should be weekday, weekend. Weekday, weekday, and weekend, weekend. This is lean, obese from the weekday, lean and obese at the weekend. So this is the number of active bouts that the kids had per day, and they are hundreds of them, but the mean duration is about 13 seconds. And you can see at the weekend, doesn't matter whether you're lean or obese, your number of your bouts declines, but it's significantly less in the obese, either in the weekday or at the weekend. The duration of the bouts went up at the weekend. The intensity of the bout stayed about the same. And this is interesting. This is the duration between the bout intervals. So if we look at the obese, they have many, many more. They have a much longer period between bouts than that sitting period. So we can make sense of the data by trying to do this, but to collect these sort of data, you really have to love the kids through the process. And these data were collected over 21 days, so it was a hugely laborious study. Okay, before we touch on sedentary, I want to just touch on subjective measures, which would be self-report. And I think the most important piece is that self-report instruments overestimate physical activity by about 72%. It's crazy. So the validity of estimates using self-report, either for overall activity or for moderate to vigorous physical activity, is really low. But some argue that the objective measures could be complemented by the self-report, because the self-report might tell you what the kids are doing, not just how much activity they're doing. But we don't use it because kids are notoriously bad at remembering what it is that they've done. So the last is sedentary. And if I was to have asked you to recount the times that you were sedentary yesterday, it would have been exceptionally difficult. And I don't think you would have even got close to what reality was. So physical activity is not valid. Sedentary is definitely not valid. And the only surrogate we use these days is screen time. And we're going to come back to that as a workshop. But is screen time really a valid substitute for sedentary behaviour? So we don't remember this or this. We don't remember when we broke it up with incidental. It's not planned, so it's hard to remember. And if adults find it hard to remember, kids find it impossible. So we do have devices that can measure sedentary. And remember, in class last week, we spoke about these devices. There were two attributes of sedentary that we needed. One was posture, and the other was a low amount of energy expenditure. So this device here is worn at the thigh, and when this kid is sitting, the thigh is horizontal, so the device knows that the thigh is sitting. When the child stands, the thigh is vertical, so the device knows the child is standing. And it's got an embedded accelerometer, so once the kid starts to move, if it's vertical and they're moving, they know that it's movement. It can distinguish standing from movement. So this is a study Kate's conducting, where she looks at the impact of a prolonged period of sitting in the lab on the superficial femoral artery. But what I want to just draw your attention to is this device. So it's taped, you can hardly see. It's like a second skin tape. It's taped to the child's leg. So it's waterproof, they can wear it. And because it's taped to the leg, they tend not to take it off because that tape is hard to get off. And this is what this device gives us. It's a very clever little device. This device was worn Thursday to Thursday. Blue is sleep time. So they if you look at this, you can see these are each of the days. Let's say take on Friday night, the kid went to bed at this time, you can see here, and then they've slept all the way around to here. This is probably around 8 a.m. And then the yellow is sedentary time, red is active time, and green is notional, also active time, breaks in movement. So you can see that this kid has gotten up, that's the green, then they've done something quite sedentary, then they move a bit, they do something more vigorous, then they sit, lots of movement here, sit. But let's take this day, for instance. This is quite heavy loads of, this is at school, right? They go to school, probably walk to school, this kid. Played in the playground, then they sit. They may have moved between classes, they sit, probably have break time, then they sit all the way around, and you can see how much sedentary time they accumulate. So this gives us a really good valid indicator of sedentary time that we can use nowadays. So the measurement of physical activity and sedentary time is complex. It does require device-worn measurement. Self-report is just not good enough. But what device is only really answered by the answer to a question, what are you wanting to measure? What's the question that you're trying to get at? If you're measuring cardiovascular health, then it would be better to measure cardiovascular strain, so I would use a heart rate monitor. If you really want to get at sitting, you need to wear one of these devices at the leg so we get posture. So that, again, it's all of these device worn, but you need to wear a device. So there's a reading for this section, this first section, which is a bit of an old chapter now, but it gives a very nice overview of physical activity, brings in the concept of NEAT, non-exercise activity thermogenesis, all the stuff that the kid does that's not planned, it's the unplanned part of their physical activity, and talks about it in context to health issues, particularly to obesity. Okay, enjoy the reading.